All right, guys, so this is a review of the Chapter 4 stuff. So I'm going to run through the problems that I gave you. The first one I believe that I gave you was number 5. So we're going to take a look at that, and like I said, just kind of run through. So if there are things that you had more questions on than others, you know, feel free to skip around, do whatever. So we're going to start with number 5. Okay, so this is one of those linearization approximation ones. So we are trying to approximate this value right here. And of course, the main idea that I gave you is like, oh, we're trying to pretend like we can do this without a calculator or something. The point is that we're able to use tangent lines to kind of approximate something. So what we want to do is we're going to take this and come up with a function. So the function that we are going to use is 1 over x at the point x equals 1, because of course we know what 1 over 1 is, and then we can use that to approximate what the function value would be at 1.02, which is obviously very, very close to the point of tangency. So we start by plugging 1 into the original function. Of course we get 1, and so this is the point of tangency. Point of tangency that we're talking about is the point 1, 1. And so we have a tangent line that goes from that curve. Anytime that I'm really, really close to that point, like if I plug in 1.02 for instance, I'm going to have a pretty close y value, but of course never perfect. So now I want to find the slope, f prime of x. So this of course I can think of as x to the negative first. So when I take the derivative, the negative 1 comes out front, and then the power drops down to a negative 2. So this is negative 1 over x squared. So that's the slope. That's the derivative. I use the derivative to find the slope at one particular point. This is something that you guys have been messing up for weeks and weeks now. You can't just use this function in your tangent line. You have to use the actual slope, which you get by plugging in the actual x value. So this gives us a negative 1. So the slope is negative 1. We're going to plug that into a tangent line. So y minus, the y value was 1, equals the slope, and then times x minus the x value. All right, so in this section we did something slightly different. We actually did get y by itself, so we could do the linearization. So I have y equals negative x plus 1, so negative x plus 2 is my tangent line, and I can write that as the linearization, so negative x plus 2. So what I do to approximate what 1 over 1.02 would be is I plug 1.02 into the linearization, or the tangent line approximation. All right, so this gives me 0.98, which sounds like it could be pretty close to accurate. Like 1 over 1.02 would just be slightly less than 1, so about 0.98. And then what we want to do is use a calculator to estimate the error. So what I'm going to do is, this is my formula, big absolute values. So here we go. Oops, there it is. Absolute value, and then I put in here the estimate, which is 0.98, and then minus the actual value, 1 divided by 1.02, and then over the actual value, 1 divided by 1.02. And then I always multiply it by 100 so I can get a percentage. Okay, so it comes out to be exactly 0.04. So the percent error equals 0.04% error. So that is my error, that is my approximation. All right, next one is number 7. We are finding a linearization. Remember, I will say this over and over again. Linearization is the exact same thing as a tangent line. So we start with y equals the square root of x, and we are trying to find it at a equals 25. So this one actually is less work than the previous problem was. All I need to do is come up with the tangent line itself. So my function is this right here. So first I want to find the point of tangency. So I plug my x value into the function. That of course gives me 5. And so the point of tangency is 25 for x, 5 for y. And so that's the xy value that I plug into my point slope form when I'm finding the tangent line. Then I need to find the derivative. And I use the derivative to find the slope of the tangent line at this point right here. So the derivative, 1/2 comes out front, and then the power drops down to a negative 1/2. This is a very simple function, so I don't have to do a chain rule. So then I find the derivative at 25, so 1/2, and then times 25 to the negative 1/2. 25 to the negative 1/2 is 1/5, and 1/2 times 1/5 is 1/10. So that is my slope at that particular point, which if you picture a square root function, it's got a very, very not steep negative slope. So 1/10 sounds about right. Did I say negative? Positive. Not steep, positive slope. So y minus the y value, which I found to be 5, equals the slope, and then times x minus the x value. Okay, so since we are finding a linearization, we want to get it back into slope-intercept form. So my linearization is 1/10 times the quantity x minus 25, and then plus 5. If you wanted to, you could distribute that 1/10, add the 5. You'd have to combine some like terms. You could do it, of course, if you wanted to. I'm just telling you it's not necessary. So if I do negative 25 over 10, that would reduce down to negative 5 over 2, or negative 5 halves. And then I could add the 5, and I would get positive 5 halves. So you could do that. Either way, you could do like a slightly weird version, not quite point slope, not quite slope-intercept, or you could actually get into slope-intercepts. Either way. But this is what we're looking for the linearization, one or the other. All right, next one, we're going to go down. It's kind of a weird story problem. This is number 16, still kind of in the same category as these linearization problems. So this says a store sells 80 MP4 players next week when the players are priced at $75. Okay, so when their price is $75, we sell 80 of them. Estimate the number sold if P is raised to $80. Assuming that, so we want to know what happens here, assuming that the rate of change of the number you sell with respect to the price equals -4. So what this means right here, the rate of change of n with respect to P means the number that we sell goes down 4 every time the price goes up 1. Okay, so the number that we sell goes down 4 every time the price goes up 1. It's like a slope thing. Okay, so if my price goes up $5, that means the number I sell is going to go down 5 times -4, which is 20. So it'll go down 20, which goes down to 60. So what we have here is every $1 increase in price, I lose 4 MP4 players. Okay, so when I go up 5, this goes down 20. And then it says, estimate N if the price lowered to $69. So if I go down to $69, that means that I'm decreasing the price, which means the number that I sell should be increasing. So if I am decreasing the price by $6, that means this will actually go up 4 times 6, which is 24. So the number that I sell should actually go up 24. So from my original of 80, it'll go up 24 to 104. So it's kind of a weird play on what the slope thing means. Okay, next one after that, we're going to start doing some Rolle's theorem, mean value theorem, things like that. So number 20 and then number 21 are the same type of problem. So show that f of x equals 2x cubed plus 2x plus sine x plus 1. Whew. Has precisely one real root. So this is an application of Rolle's theorem. It's kind of a weird application of Rolle's theorem. What we do is to prove that it has only one root, we kind of assume, or like okay, so let's say for now that we actually have 2 real roots, and then we prove that that can't possibly be true, okay? So we are going to assume, I guess, that we have one real root. So let's find one place where this is below the x-axis and one place where it's above. So let's start with f of 0. If I plug in 0, this is 0, this is 0, this is 0. That, of course, is 1. And so f of 0 is 1. And then I can find a value where I get a negative value. So let's try -1. F of -1, I get a -2, another -2. This is a positive 1, and then sine can't possibly be any more than 1 no matter what. So we know that this is going to come out to be negative. Doesn't really matter what it is. Okay, so we start off with that. We've got one positive value, one negative value. So according to the intermediate value theorem, we know that f of x has at least one root somewhere on that interval. Okay, so somewhere on that interval, we know that f of x has at least one root. What we're trying to do is prove that it has exactly one root. All right, so let's say that it has a second root. we'll call it B. So we'll call this one A, we'll call this one B. What that would mean is that f of A would be the same as f of B, which would of course be 0. If they're both roots, they're both x-intercepts. If I plug in A or if I plug in B, I get 0. So according to Rolle's theorem would imply that somewhere on that interval I would have a slope of 0. Because Rolle's theorem says if two y values are the same and your function is continuous, somewhere in between you must have a slope of 0. So here's what I do. I take the derivative, f prime, and I get 6x squared plus 2 plus cosine, and then, 0. I want to show that this is equal to 0. Okay, so now this is not something that we ever want to handle on our own. That's not really math that we could do necessarily. But this thing right here, what I do know is that this is always going to be positive. Let's make some notes here. This is always going to be positive. 2, of course, is positive. And then cosine is going to be somewhere in between -1 and 1. Okay, so that's what we know. So this is going to be positive. I mean, it could be like barely positive. But if this is 2, so here's what we've got. This is something positive. This is 2, which of course is positive. This is never ever going to be smaller than -1. So even if this is at its minimum, this will be at 2. These two automatically together will always be positive. So the combination of these two things will always be positive, and this thing will always be positive. So this is never ever going to be equal to 0. This function, f prime, is entirely positive no matter what. So the derivative is never equal to 0. So we're like, well, wait a second. If there's a second root, then there must have been a slope of 0 in between. So what does that mean? Must mean that our assumption is wrong and that there is no second root. So our conclusion would be there is no second root, which we called B, and so therefore f of x has exactly one root. We should say one real root. There's always the possibility of complex or imaginary roots. Okay, next one is number 21, the very next one. This is a little mean value theorem application. Okay, so 21, oops, I flipped the page, hold on. I think it is mean value. There it is. Okay, verify the mean value theorem. Okay, so this is a really good application. We want to verify the mean value theorem for this function, just the natural log of x, nice easy function, on 1 to 4. So what the mean value theorem says is that the slope of a secant line from point to point is going to be the very same as some tangent line on that interval. Okay, so you always start mean value problems like this. You start with the slope of the secant line, like this. So f of 4, that's the natural log of 4, minus the natural log of 1, and then over 4 minus 1 is 3. So the natural log of 4, that is the power on e that gives us an answer of 4. I don't know what that is, so we're going to write down the natural log of 4. And then here, natural log of 1 is the power on e that gives us 1. That's 0. So natural log of 4 minus 0. Now this is the natural log of 4, which is one quantity, divided by 3. It is very different from the natural log of 4/3, so be careful there. So that is the slope of my secant line. What I do now is I want to find where I would get a parallel tangent line. So I want to know when my derivative would be the same. So I take the derivative of the natural log of x. Derivative of natural log of x is just 1 over x, one of our easiest derivatives. And so I set my derivative equal to the average rate of change. Okay, and this is going to be kind of ugly just because I have the natural log. I'm going to cross multiply. And so I get x times the natural log of 4 equals 3, and then I divide both sides by the natural log of 4. Okay, so my x value is 3 divided by the natural log of 4. Just to confirm, we want to make sure it actually is on that interval. So 3 divided by the natural log of 4, it is. Whoops, that doesn't show. There we go. It's about 2.164, so that is on our given interval. So that's what you do. When you confirm the mean value theorem, you come up with the actual value that makes it work. And then you do want to make some sort of statement about this function being continuous and differentiable, because you need those two things to happen in order to even use the mean value theorem. So again, you need to make a statement about f of x being continuous and differentiable. Okay, so now we're going to go on to some of these min and max problems. So we've got 25 and then 29 in that next section. So the instructions read, define the critical points and determine whether they are mins, maxes, or neither. Okay, so 25, f of x equals x cubed minus 4x squared plus 4x. So to find critical points, what we do is we take the derivative and we find where it is either equal to 0 or undefined. So the derivative is 3x squared minus 8x plus 4. Okay, so we're going to try to find, first of all, we always take a quick glance to see where it's undefined. This is a polynomial. It's never going to be undefined. So now we set it equal to 0. Let's see if this thing has, if it's factorable. Start with 3x and x. So I know they're both going to be negative because they multiply to a positive 4 but add to a negative 8. So let's do, maybe this isn't going to work. Oh yeah, well, okay. 2 here, 2 here, because then I get negative 6 and negative 2, and that gives me my negative 8. Okay, so I set these both equal to 0 and solve, and so I get a nice 2/3 and 2, and those are my critical points. And now I need to determine whether my critical points are mins, maxes, or neither. So we have 2 different tests that we could use, and I'm going to show them both, just so you know, because we could do the first derivative test for local extrema, or there's the second derivative test for local extrema. Like I said, I am going to show them both. So the first derivative test, what you do is you set up a sign chart. Remember, we always label our sign charts with what it is a sign chart of. Put our critical points on here. In the first derivative test, we look for a sign change, either positive to negative or negative to positive, to tell us if we have any local extrema. So I'm going to plug in something to the left of 2/3, you know, something like 0. If I plug 0 into my first derivative, I get something positive. Then I could plug in 1 right here. So if I plug in 1, I get 3 minus 8 plus 4. That comes out negative. And then if I plug in something bigger than 2, you know, I could plug in like 10 just to make it extra obvious. Then I have 300 minus 80 plus 4. That is definitely positive. So the first derivative test tells me that 2/3 is a max. And that's because, I'm not going to write these explanations down, but you do need to know how to give the explanations. You'd write because f prime changes from positive to negative there. So that means my function is increasing, then it's decreasing, and that would leave a max. And then x equals 2 is a min for the exact opposite reason. And again, I'm not going to write it down, but you need to know how to explain this. You'd say that 2 is a local min because f prime changes sign from negative to positive there. Okay, so to give you a visual again, f would go from decreasing to increasing, which would leave you with a min. So that's one way to check. Another way would be the second derivative test. And the way we use the second derivative test is by first taking the second derivative. And so I take the derivative of this, I get 6x minus 8. And then I actually plug in my critical points to check the sign. So if I plug in 2/3, 6 times 2/3 is 4. And then minus 8, that of course comes out negative. And so if my second derivative is negative, that means my graph is concave down. If my graph is concave down, that means I have a max. So 2/3 is a max by the second derivative test. If I plug in 2 into my second derivative, 6 times 2 is 12, minus 8, and that comes out positive. So if my second derivative is positive at that point, that means my graph looks like this. And so any critical point that I find would be a min. So according to the second derivative test, I get the very same answers, which should make sense as long as I'm using those tests appropriately. All right, next we're going to do a similar problem in that same set with the same directions. This one, though, is a non-polynomial example, so I wanted to show this to you as well. So a function of theta, this is sine squared theta plus theta. So same directions. I am going to find the critical points and determine whether they are mins, maxes, or neither. So I start with G prime. That's how I'm going to find my critical points. This requires a chain rule. Remember what this really actually is sine of theta quantity squared. Okay, so 2 comes out front. I leave my sine theta exactly where it is, and then I multiply by the derivative of sine, which is cosine theta. And then plus the derivative of theta, which is just 1, because remember theta is the variable here. So if I want to find my critical points, I set this equal to 0 and solve. And so what I'm going to do is I will subtract 1, divide by 2, try to solve for theta. Okay, so subtract 1. divide by 2. Okay, so this is weird, for sure. This is a very weird one. I want to know when the product of sine times cosine is equal to a negative 1/2. Okay, so again, I want to know when the product of sine and cosine would be a negative 1/2. Okay, and that is going to happen somewhere in the pi over 4 family. So picture if you have positive root 2 over 2 times a negative root 2 over 2, and this is just knowledge of your unit circle. You end up with a negative 2 over a positive 4, which of course is negative 1/2. So we need to know where one of them is positive root 2 over 2 and where one of them is negative root 2 over 2. That happens first in the second quadrant. In the second quadrant, cosine is positive, but sine is negative. Sorry, vice versa. Cosine is negative, sine is positive. And then it happens again at 7 pi over 4, where sine is negative and cosine is positive. So those are your critical points. Again, basically just requires knowledge of the unit circle. Okay, so I could do the first derivative test. You'll never have to do both. I'm just giving you a good example of both. It will tell you which one to use, which is why I want you to see both of them. So I have 3 pi over 4. And I have 7 pi over 4. I like showing you these trig ones because it gives us practice on knowing our unit circle. So if I plug something in here, I could plug in 0. I could plug in pi over 4, something like that. If I plug in pi over 4 into here's my first derivative here. I have 2, and then times a positive, plus 1. That has no choice but to come out positive. If I plug in, pi over 2 would be a good example. That'd be an even easier example because cosine would be 0 if I plugged in pi over 2. So this would be 0 plus 1, which definitely comes out positive. In here, let's use pi. Pi is a great example. So if I plug in pi, the sine of pi is actually also 0. And so if I plug that in, pi, I get 0 plus 1, which also comes out positive. And then if I plug in something beyond here, you could use the 11 pi over 6, something like that. I wouldn't use 2 pi just because we kind of have this natural barrier here of 0 and 2 pi whenever we're talking about trig values. And so if we plug this in, something like 11 pi over 6. So 2, and then the sine of 11 pi over 6 is negative 1/2. And the cosine of 11 pi over 6 is positive root 3 over 2. And then plus 1. So basically, we just need to know if this is going to overtake the positive 1. And so multiply everything out. I'm going to get a negative root 3 over 2 plus 1. Negative root 3 over 2 is actually bigger than 1. And so this overtakes it. This does come out negative. Okay, so that will be negative. So last thing that I need to do is identify where my maxes and mins are. And so if I do this, plug this one in right here, because this is the only sign change, I would say that x equals 7 pi over 4 is a max. And again, you would have to write the AP explanation. It is because f prime changes from positive to negative there. Okay, let's do a second derivative test. We take the second derivative. G double prime is equal to, and then I would have a product rule here. So 2 times sine, and then times the derivative of cosine is negative sine, plus cosine times the derivative of 2 sine, which is 2 cosine, and then plus 1, the derivative of 1 is 0. So this is negative 2 sine squared plus 2 cosine squared. So what I do is I plug in my 2 critical points to see if my second derivative comes out positive or negative. So I plug in 3 pi over 4. That's the first thing. Plug in 3 pi over 4. And so I get negative 2. Sine squared, 3 pi over 4 is a positive root 2 over 2. And then I square it. Plus 2, and then cosine squared comes out to be root 2 over 2 squared. Okay, so when I plug all that in, I know that these two things are the exact same, so I'm going to come out with a 0. So this is some weird thing about the second derivative test, and we have this written in our notes as well. When we are doing the second derivative test, if my second derivative comes out to be 0, what we wrote down for that is that the test is inconclusive and that we need to try another method. Okay, so we already did try another method, so we just leave it, and we know that according to this, I got neither a max nor a min, which actually, I guess I should write that. This is neither a max nor a min. All right. Okay, so now let's go back to this second derivative test. This is 7 pi over 4. So what I'm going to do is I'm going to plug in 7 pi over 4. And so I have negative 2. This would be a negative root 2 over 2 squared. Actually, that's negative as well. It comes out the same, though. 2, and then this is a positive root 2 over 2 squared. Again, those two things come out to be opposite, so I get 0. So I came up with 0, so again what that means that the second derivative test is inconclusive, so we go back up to the first derivative test, and according to what I wrote down here, oh my gosh, square root of 3, not bigger than 2. So when I take the square root of 3, it comes out to be something less than 2. Shoot, so this is actually positive. Okay, that's positive. This is positive, and so this is also neither. I have no sign changes happening here whatsoever. Okay, so these are both neither. Let me show you that graph, just so we can get a visual here. Okay. Here it is. So we've got lots of places where it zeroes off, but not actually a max or min. It's either increasing or stopped the entire time. So here's that 3 pi over 4, stopped but continued increasing. Here's that 7 pi over 4, stops but continues increasing. All right, so sorry about that. Just mind blank on that part. Okay, next problem that we're going to do, we're going down to the next section where we're going to find the extreme values. Those are the absolute min or maxes, and we do the absolute min or maxes slightly different. When you've got a closed interval, you're always doing absolute. So even though the directions don't say absolute min or max, giving you the closed interval is the clue. All right, so 31 and then 37 in this section. This one, avoid a product rule at all costs. Just multiply this out, and then I don't have to do a product rule. Please keep an eye out for that. Any little algebra simplifications that you can do. And the interval that they gave us is this. So remember, absolute extrema can happen at endpoints and critical points. So I can test the endpoints. I'll do that in just a moment. And then I can test the critical points. So I start by finding my critical points, which I do by taking the derivative and setting it equal to 0. So my critical point that I come up with is 5. However, even though it is a valid critical point, it is not on this interval. So I don't use it at all. So I'm just going to test my endpoints. So I set up a little table. I plug in my endpoints, and then normally I would plug in my critical points, but didn't come out to be in our interval, and we only had one of them. So I plug these into the original function. Every time I'm doing this table for absolute mins and maxes, I plug it into the original function because I want to know what's the absolute highest y value, what's the absolute lowest y value, and we can only get that by plugging into the original. So I plug in -1. I would have -1 times 10 plus 1, which comes out to be a -11. And then 3 would be 3 times 10 minus 3. 3 times 7 would be 21. So I'm looking for the extreme values. So the minimum value is -11. The maximum value is 21. Always read carefully because sometimes the AP test will say, like, at what x value does the minimum occur? Then you would say -1. But if they want the extreme values, they want the minimum value and the maximum value. That's the y. Okay, next one. Same topic. Number 37. Okay, so this one is given on the interval from 5 to 40. So I start by finding my critical points. So I take the derivative, I get 1 minus, and this will be 12 over x. So critical points are anywhere my first derivative is either equal to 0 or undefined. So it's undefined at 0. So if I plug in a 0 here, it would be undefined. And it would be equal to 0 at 1 minus 12 over 12. So 12 is my other one. Okay, looking at the interval, this one does not count because it doesn't fall in the interval. So I'm going to check my 2 endpoints and my critical point in a table. So again, where do absolute extrema occur? Could be endpoints or critical points. So I'm going to plug these into my original. So I've got 5 minus 12 times the natural log of 5. Now, of course, we always like exact values if possible, but you have no idea which one comes out bigger if we don't get at least a decimal approximation. So calculator page, so start with 5. So into my original function, 5 minus 12, oops, that is not 12, the natural log of 5. Okay, so there's my first value. Then same thing with 40. 40 minus 12 times the natural log of 40. And then one more time with the critical point, 12. 12 minus 12 times the natural log of 12. Those are my values. So I can plug these into my table and just write them all down. So here, and always 3 decimal places, 14.313, negative 4.267, and negative 17.819. So again, they ask you for the extreme values. So the minimum value would be the negative 17.819, aka 12 minus 12 times the natural log of 12. The maximum value is still a negative, but it's the largest one. That is about negative 4.267, or 4 minus 12 times the natural log of 40. Okay, we've got our exact values and our decimal approximations. Okay, so we've got that section down. Next, we are looking at a picture, so I'm going to slide the book right under here. So for number 40, match the description with the graph of its derivative, f of x. So if f is increasing, first of all, that means the derivative is positive, so this one's out. If f is concave up, that means that f prime would be increasing. So to match these characteristics, f prime should be positive and increasing, and that's Roman numeral number 2. So A is Roman numeral number 2. For B, if f of x is decreasing, that means f prime is negative, and if f of x is concave up, that means f prime is increasing. So f prime should be negative and increasing. That's this one. So B is Roman numeral number 1. And that, of course, leaves C for 3, but let's just recap. F prime should be positive and decreasing, and that matches with this one right here. So, all right, so C, of course, matches with 3. We're going to move right to that next one, number 41. We're going to find inflection, concavity, all of those sorts of things. So our function is y equals x cubed minus 4x squared plus 4x. So for this one, we want just the points of inflection. And so not the possible points of inflection, but the ones that actually turn out to be points of inflection. So y prime, and then I need y double prime. And now this is actually the same function that I had in number 25. So we've got the second derivative for this already, but we are just going to show the work one more time. So that is our second derivative. Inflection points happen when the second derivative changes sign. So I start by either setting the equal to 0 or where it's undefined, but since this is a polynomial, it's never undefined. So this is going to occur at 8 over 6, which is 4 over 3. Okay, so that is my one possible inflection point. Until you do a sign chart, we don't know if it actually is or not. So this is a sign chart for y double prime. I have just one possible inflection point. So I can plug in different values. Say I plug in 1 or say I plug in 0. If I plug that in here, I get something that's negative. Then if I plug in something, I could plug in something like 10 or 100. 600 minus 8, definitely positive. So this does come out to be an inflection point, and that's because the sign of my second derivative changes, which means the concavity of y will change. Y will go from concave up to concave down. All right, I think we've got another one in this section, right? Yeah, 45. So same question, the inflection points. Okay, so this one requires a product rule. So for the first derivative, I've got the first, which is x squared minus x, and then times the derivative of the second. That one requires the teeniest little chain rule, and that is going to be negative e to the negative x, because the derivative of negative x is a negative 1. And then plus the first times the derivative of the second, which is a 2x minus 1. Okay, so what I'm going to do is I'm going to factor out an e to the x so that I can simplify this up so I can avoid like a double product rule. So in parentheses, I can distribute this negative to these things right here. So I have a negative x squared. This would be a positive x combined with this positive 2x, and then this minus 1. So just rearrange my function by factoring out an e to the negative x, and like I said, I can avoid a double product rule. So take the second derivative. So here's my first function, here's my second function. So the first times the derivative of the second, and then plus the second times the derivative of the first, which is again a negative e to the negative x. Okay, so let's factor out that e to the negative x again so that I can get my possible inflection points. So e to the negative x, I can distribute this negative to these pieces here. So I have a positive x squared, a negative 3x combined with this negative 2x, and then a positive 1 combined with this positive 3. Okay, so that's my second derivative. What I'm going to do is I'm going to look to see where it's undefined. It will never be undefined because exponential functions and polynomials are always defined. I can set this equal to 0, which means I can set all of my pieces equal to 0. This thing factors down to x minus 4, x minus 1. So exponential functions will never be 0. That gets me nothing. But I do get 4 and 1. So those are my potential inflection points. Remember, we need to actually check for a sign change. So I'm going to set up a sign chart with f double prime. Okay, so I can plug in something like 0 into my second derivative, which I get right here. So this thing right here, always positive. An exponential function like that, as long as it doesn't have a negative out front or anything, will always be positive. E to the 0 is 1. And if I plug 0 in here, I get 4, and so that comes out positive. I could plug in something like 2. Again, this will always be positive. If I plug in 2, I get 4 minus 10 plus 4. That comes out negative. And then something bigger, something like 10. Again, always positive. And then 100 minus 50 plus 4 comes out positive. So I do have two sign changes. So 1 and 4 both turn out to be inflection points. Okay, so now we are on to the next page, and we've only got a handful more left. We're on to number 47 on the next page. Okay, so what we're doing at this one is we're doing some graphing. So I've got y equals 12x minus 3x squared. So lots and lots of little pieces and features that we're supposed to be looking for. Transition points are either critical points or inflection points. So I start with first derivative, and I can do the second derivative. Okay, so critical points are going to happen when this is either equal to 0 or undefined. So my critical point, I just have 1. It's x equals 2. And then this second derivative is always negative, which means my original graph will always be concave down, which should make sense looking at this. It's just a parabola. Okay, so I only have one critical point, which is either going to be a max or a min. Spoiler alert, it's going to be a max, because I know that this is an upside down parabola. But we're just getting some of the key ideas here. Okay, so I'm going to set up a double sign chart here. One for y prime, one for y double prime. My only transition point is 2. That's the only place where the shape might change. So in my first derivative, I plug in something to the left of 2. So if I plug in 0, I get a positive. If I plug in 3, I get a negative. So my graph goes from increasing to decreasing. And then I know that my second derivative is always negative. So negative all the time, no matter what. So my graph goes from increasing in concave down to decreasing in concave down. What that means is I have a max at 2. So let's plug 2 into the original function to get that actual value. So 12 times 2 is 24, and then minus 3 times 2 squared is 12. So when I'm plotting this value, my x value is 2, my y value is 12. Let's scale this. 6, 8, 10, 12. So I've got that. I also want to find like x-intercepts, y-intercepts, things like that. So let's set this equal to 0 to get y-intercepts. I can factor out a 3x. Okay, so I get 0, and I get 4 for my x-intercepts. And so now 0, 0 is also my y-intercept. So this is my graph, kind of a narrow upside down parabola. So I've got my max, I don't have any inflection points, and there's no asymptotic behavior because it's a polynomial, it's not rational. Okay, we've got one more of these, and then that one weird little draw your own graph problem. So 55 is another graph. Okay, so the graph is y equals root 3 sine and then minus cosine. And we are only graphing it from 0 to 2 pi, so we only have to go through one cycle. Okay, so start with the first derivative. First derivative, my constant root 3 stays right there. Derivative of sine is cosine. And then the derivative of cosine is negative sine, so this will be plus sine. Equals 0. So there's never any place where this will be undefined because cosine and sine are always defined. But what I want to do is I want to subtract, try to get the x by itself. And again, this just requires knowledge of your unit circle. It's really all it is. And so I'm going to, I might as well solve for sine. I guess it doesn't really matter. So sine equals negative root 3 times cosine. So thinking of some of those unit circle values, some of your pairs, they're either both root 2 over 2, or one's 0 and one's 1, or negative 1. We've also got these different pairs where you've got a 1/2 and a root 3 over 2, or a root 3 over 2, 1/2. All right, so the 1/2 root 3 over 2, that happens at all of the pi over 3 family members. And then the root 3 over 2, 1/2, that happens at all the pi over 6 family members. So what this is saying is we want the value of sine to be negative root 3 times the value of cosine. Okay? So that means we want the sine to be negative root 3 over 2, and we want the cosine to be 1/2. And that way, if this is 1/2, then the sine is negative root 3 over 2. Or vice versa, like this one could be positive and this one could be negative. Something like that. Okay, but they need to be opposite signs. So that happens in this grouping right here. No, it doesn't. That happens in this grouping right here. I was looking at sine first. All right, so at the pi over 3 family members, they need to be opposite signs. So in the second quadrant, they're opposite signs. So that is 2 pi over 3. At 2 pi over 3, the cosine is negative 1/2, and the sine is positive root 3 over 2. And then again in the fourth quadrant, which is 5 pi over 3, at 5 pi over 3, the cosine is positive 1/2, and the sine is negative root 3 over 2. Okay, so those are our two critical points. Possible inflection points. We take this, the first derivative, and take the derivative again. Okay, so we get negative root 3 times sine plus cosine. We want to set that equal to 0. Again, there's nowhere else where it's undefined. So what I'm going to do here is I'll add this term to the other side. So we want cosine this time to equal positive root 3 times sine. So whatever the cosine is, we want it to be root 3 times the value of sine, which means we want sine to be 1/2, and we want cosine to be root 3 times 1/2, which is root 3 over 2. Or they could both be the negative versions. Okay, so that is going to happen here. So at pi over 6 in the first quadrant, they're both positive. And then at 5 pi over 6, 7 pi over 6 in the third quadrant, they are both the same sign. One is negative root 3 over 2, one is negative 1/2. Okay, so those are my possible inflection points. So I'm going to set up a really nice double sign chart here. Okay, so I have this natural marker at the end here, 0 and the 2 pi. Okay, and then this one, I'm going to kind of extend everything a little bit. So f double prime is blocked here, and then again, right about here, it's 7 pi over 6. We need to know what order they fall in. And then 2 pi over 3 would be right about here. And then 5 pi over 3, right about here. Okay, so I'm going to check just the sign change of f prime, then the sign change of f double prime, and then I'll kind of extend those lines and make one big sign chart. Okay, so let's check something in here. And so I could use, since this is in the second quadrant, I could use pi over 2. Pi over 2 would be a good example. So into my first derivative, root 3 times 0, and then plus 1. So that comes out to be positive. In here I could use pi. Pi is a great choice as well. So I have root 3 times negative 1 plus 0. So that's negative. And then something beyond here. 5 pi over 3 is already in the third quadrant. So these ones get kind of ugly. Really my only option in here would be, I could use like 7 pi over 4. So let's do a little side work for that. So 7 pi over 4, root 3 times the cosine of 7 pi over 4 would be positive root 2 over 2. And then plus the sine of 7 pi over 4 would be a negative root 2 over 2. So this comes out positive. I know that just because I know this is going to be bigger than that is. Okay, then a sign chart on f double prime. Okay, so here is my second derivative. So here, this one's kind of a bummer because this is really the first value that I know on my unit circle. But let's kind of play around with this in here. Okay, so I have negative root 3 times sine. Now, we're gonna play around a little bit here. Sine of pi over 6 is 1/2. If I go lower than pi over 6, this is going to be something less than 1/2. Okay, and then plus cosine, picture my unit circle, if I go if I go smaller than pi over 6, if I'm going on my unit circle, like I'm headed from pi over 6 back down this way, my y value gets smaller, my x value actually extends out a little bit. So the cosine of pi over 6 is root 3 over 2, but this is going to be something bigger than root 3 over 2. Okay, so this is kind of messy. So I've got something that'll be smaller than negative root 3 over 2, plus something that'll be bigger than positive root 3 over 2. So something smaller plus something bigger means that the bigger one is going to overtake. All right, the positive one. So this will be positive. That one's kind of messy. Okay, and then something in here, we could use pi. Yeah, let's use pi. Okay, so plug this in here. I've got negative root 3 times 0, and then plus negative 1. So that comes out negative. And then something beyond here. So I could use, since this is in the third quadrant, I could use 3 pi over 2. So I have negative root 3 times negative 1 plus 0. So that comes out positive. Okay, so now let's extend this sign chart a little bit. All these values. Okay, there we go. So this is still positive here. This one's still negative here. This is positive. And then this, we'll write the negative in both places there. Okay, so now we've got our 1, 2, 3, 4, 5 different intervals. Okay, so all sorts of different things that can happen here. We're going to have all sorts of lovely values that we can work with. So we've got pi over 6, 2 pi over 3, 7 pi over 6, 5 pi over 3, and of course the endpoints of 0 and 2 pi.